Hi guys, today we're going to talk about dividing radicals. So our essential question today, we have two of them. The first is, what does it mean to rationalize a denominator? And the second essential question is, how do we remove radicals from the denominator? Okay, so we have two rules. The first rule is you can never leave a radical, so the square root symbol, in the denominator. That is mathematically illegal. You can never have a radical in the denominator. And secondly, you can never leave a fraction under a radical sign. So our final answer can't be like the square root of 1/2. So we've got three examples. We need to know if they're okay. This one, does it break any of the rules? No, it doesn't have a radical in the denominator, and it doesn't have a fraction underneath the radical. The fraction is the whole problem, but the only thing under the radical is the 3. So yes, this is okay. Second one, is this okay? No, this is not okay. It breaks the first rule. The first rule is that you can never leave a radical in the denominator, and this has the square root of 2 as its denominator. So no, breaks the first rule. And the third one, the square root of 1/2, is that okay? The answer is no. We are square rooting 1/2, and 1/2 is a fraction. I can never leave a fraction under the radical sign, so it breaks the second rule. So we know our rules. Now we need to learn something called rationalizing the denominator. So what does it mean to rationalize the denominator? Well, there we go. What it means is that you're going to remove radicals from the denominator. That way you can have a problem that actually complies with rule number 1. So you want to remove radicals from the denominator. And the way that you do that is you multiply the numerator and denominator by some quantity that makes the radicand, or the number under the radical, have an exact root. You want it to be a perfect root. So in example 1, we're breaking the first rule. So you can't have a radical in the denominator. We're breaking that rule. So in order to rationalize, you want to multiply the numerator and the denominator by something that'll give the radicand an exact root. So you can't take the square root of 3. However, you can take the square root of 9. So I'm going to put the square root of 3 on the bottom and the square root of 3 on the top, because if I multiply the square root of 3 times the square root of 3, I will get the square root of 9. And that is a perfect root, a perfect square. Now, if I do it on the bottom and the top, that means that I need to multiply the top out. So the square root of 27 times the square root of 3 is the square root of 27 times 3. That's 81. And that happens to be a perfect root as well. And it's just a coincidence. It's not always that way. The square root of 81 is 9. The square root of 9 is 3. And this simplifies to a simple 3. We are going to skip number 2 and we'll come back to it. I'm going to move this up. This breaks the first rule. We can never leave a radical in the denominator. So we're going to multiply by something on top and bottom. And notice that it has to be the same thing on top and bottom. Because if you have something divided by itself, then it goes into itself one time and this actually just has a value of 1. It's just going to look a little different. So it's got to be the same on top and bottom. So I'm going to multiply this by what on the top and what on the bottom. Can you guess? Here it was the same thing. Here also it's going to be the same thing. Square root of 6 times the square root of 6. square root of 6 over the square root of 6. The numerator is 2 times the square root of 6, so 2 square roots of 6. I don't multiply them together because the 2 is not under a radical, but the 6 is. And here, 6 times 6 is 36. Well, what's the square root of 36? 6, right? And look at your numbers outside of the radical. You have a 2 and you have a 6, right on top of each other. That tells you that you can simplify this a little bit more because the 2 over 6 is kind of like a fraction. So that simplifies to 1 over 3. And you have 1 square root of 6 over 3 as your final answer. Example 4. We have a radical under the denominator that's not allowed. So we're going to multiply the top and bottom by the square root of 5. 13 times the square root of 5 is 13 square roots of 5. And 2 times the square root of 25. What is the square root of 25? Well, it's just 5. And what's 2 times 5? Well, 2 times 5 is 10. So we have 13 square roots of 5 over 10. And now that brings us back to example 2, because example 2 is not breaking the first rule we mentioned, it's breaking the second rule. You can never leave a fraction under the radical sign. So the way that you deal with this is kind of the way that you deal with multiplying radicals. So if you have the square root of 3 times the square root of 3, it's the square root of 3 times 3 underneath. Well, here, if you have the square root of 2 over 9, that is the same thing as the square root of 2 over the square root of 9. You can break the radical up to the top and the bottom. And the square root of 9 is exactly 3. So square root of 2 over 3 is your answer. So that is what it means to rationalize a denominator. You typically multiply the numerator and denominator by this radical that's in the denominator. And that way you get this nice, pretty, perfect root on the bottom. So now we're going to move to the next page, which talks about something a little different. It's called a conjugate. A conjugate is two binomials, or sorry, conjugates, plural, is two binomials that have the same terms, but they have opposite signs between them. Conjugates are number pairs of the form a plus square root of b and a minus square root of b. Notice that the a and the square root of b are the same thing in each terms, but here a plus sign separates them and here a minus sign separates them. This and this are conjugates. It's a pair of conjugates. So let's do some examples. Let's say I give you 3 plus the square root of 2. What would the conjugate be? Well, it would be 3 minus the square root of 2. Same terms, different sign connecting them. Next one. Let's say I give you 1 minus the square root of 3. What's the conjugate? Well, the conjugate is 1 plus the square root of 3. You may be asking yourself, why in the world are we doing this? Why are we picking out conjugates? Why is this important? Well, conjugates are used to rationalize the denominator. When you multiply conjugates, you can cancel out the radicals, which is kind of a powerful thing when you don't want radicals in the denominator. So it's helpful to cancel them out. And I'll show you how that works. So let's find the product of 5 minus the square root of 2 and its conjugate. What's its conjugate? 5 plus the square root of 2. So let's find this product. Whenever I multiply 5 minus square root of 2 and 5 plus square root of 2, it's like binomial times binomial, so I'm going to do FOIL. 5 times 5 is 25. 5 times the square root of 2. Remember, I can't multiply those together to make 10 because the 5 is not under a radical and the 2 is. So this is plus 5 square roots of 2. Negative square root of 2 times 5, kind of the same thing, minus 5 square roots of 2. And finally, negative square root of 2 times square root of 2. Negative times positive is a negative. Square root of 2 times square root of 2 is square root of 4. So let's look at what happens. We have 25. We have 5 square roots of 2 minus 5 square roots of 2. Well, what happens here? These cancel out. And we have minus the square root of 4, which is really minus 2. And look at that. We started out with a binomial times a binomial, radicals in each one, and when we multiply them, our answer is just 23. So that's pretty powerful that we can multiply conjugates and completely cancel out radicals. So let's put this to good use. Example 5, I've got a radical under the division bar, so a radical in the denominator. That's not allowed. So I'm going to put parentheses around it because I noticed that it's something that I could write the conjugate of. I'm going to multiply both the top and bottom by the conjugate. So instead of 2 plus square root of 3, the conjugate is 2 minus the square root of 3. And whatever I multiply on the bottom, I also have to multiply by on the top. 2 minus square root of 3. Okay. So if I multiply, 2 times 2 is 4. 2 times negative square root of 3 and 2 times positive square root of 3 will cancel out. And then I'll have square root of 3 times negative square root of 3, which is just minus square root of 9, which is 3. So I'm going to give you a moment to think about that because I didn't show my work, but I talked through it. And finally, on the top, I don't really need to do FOIL because 6 is not a binomial. I'm just going to distribute the 6 to the 2 and the 6 to the square root of 3. And the only thing that there is left to do is to do the subtraction. 4 minus 3 is 1, so I don't really need to write over 1. That's redundant. That means it's repetitive. We don't need to do that. And I cannot subtract 12 and 6 because it's not 12 minus 6. It's 12 minus 6 square roots of 3. This is one term. And they're not like terms. So the answer here is just 12 minus 6 square roots of 3. This is as simplified as it gets. So what I would like for you to do is try out this one, example 7. Actually, you know what? Instead of example 7, let's go ahead and try example 6. Let's try that. So try it out. Multiply both the top and bottom by the conjugate of the denominator. Pause your video and try example 6. All right. So I made some mistakes, and I'd like to share those mistakes with you because maybe you made the same ones, and it's always a good idea to look at mistakes and learn from them. So I didn't have any mistakes when I distributed the square root of 6 to 3 and the square root of 6 to 2 to get square root of 12. But whenever I was foiling this in my head, because sometimes it's not a good idea to do the math in your head, you got to do it on paper. 3 times 3 is 9. And 3 times square root of 2 will cancel out with negative square root of 2 times 3. And then here, the negative square root of 2 times the square root of 2 is not 4, and I put 4. It's actually minus the square root of 4, which is 2. So I would have had this denominator wrong because I was thinking that it was 9 minus 4 to give me 5, and really it was 9 minus 2 to give me 7. So be careful. And then let's look at example 7. Example 7 has radicals in the denominator. And in the denominator, it's a binomial. That tells me I'm going to use its conjugate. So the conjugate of 4 minus square root of 10 is 4 plus the square root of 10. on top and bottom. On the bottom, we have 4 times 4, which is 16, minus square root of 10 and square root of 10 is 10. But look what happens on the top. I'm multiplying two binomials together with radicals, but they're not conjugates. They have the same term, but they have also the same signs. So when I FOIL this, I'm not going to get canceled out middle terms. So 4 times 4 is 16. 4 times square root of 10 is 4 square roots of 10. Square root of 10 times 4 is another 4 square roots of 10. And the square root of 10 times the square root of 10 is 10. So what this becomes is 16 plus 10, which is 26, plus 4 square roots of 10 plus 4 square roots of 10. That's 8 square roots of 10. Over 16 minus 10, which is 6. And I noticed something. I noticed that all the numbers that are outside of the radical, so the 26 and the 6, and the 8 and the 6, those are like fractions. So I can simplify them. They're all even, so I can cut them all in half. I can divide them by 2. So if I divide them by 2, 26 becomes 13, plus 8 becomes 4. I don't divide the 10 by 2 because it's under the radical. And then if I divide the 6 by 2, I get 3. And I can't simplify that anymore. So that is my final answer. So to rationalize the denominator, rewrite so that there are no radicals in any denominator and no fractions in any radical. So we have several issues in these 3 problems. In the first one, I have a fraction that's underneath the radical. So I need to take care of that. How am I going to do it? I give the radical to the top and to the bottom. I can't have a radical in the denominator though, so what do I multiply by on the top and bottom? Square root of 6x and square root of 6x. The square root of 6x times the square root of 6x is just 6x. The square root of 27 times the square root of 6x is the square root of 27 times 6x, which is 162x. And I noticed something. I noticed that 16, kind of the beginning of 162, and 2, if I cut them both in half, I get 81, and that's a perfect square. So I'm actually going to break this up into perfect square and leftovers. 162 is divisible by 81. The leftovers are 2 and the x. And I still have 6x on the bottom. The square root of 81 is 9. I notice that my coefficients are both divisible by a common factor. What are they divisible by? 3. 9 divided by 3 is 3. 6 divided by 3 is 2. No fraction under the radical, no radical in the denominator. Okay. Let's look at number 9. Number 9 can't have a radical in the denominator. So we need to multiply. Whoops. Sorry about that. We need to multiply by something that will create a perfect root. So I need to multiply by the cube root of something, but not 4x, because 4x times 4x, if I multiply that together, it'd be a perfect square, but not a perfect cube. So in reality, I need 3 of the same number under the radical sign and I need exponents divisible by 3. Because that's my index. So I have, forgive all the arrows, I have the cube root of 4x. And I can break this into 2 and 2. So what this really is the cube root of 2 times x. Well, I need 3 of the same number and exponents divisible by 3. So that means that I need a 2, and another 2. I need an x and another x squared. Because x times x squared is x to the power of 3, and that would be divisible by 3. So this is what I need. And what this gives me is 2 times 2 times 2, and x times x times x. And if I cube root that, I get 2x. And over it is 4 cube roots of 2x squared. I have a 4 on top and a 2 on bottom. That looks like a fraction to me. So if I divide 4 by 2, I get 2. And I still have the x on the bottom. Okay, last problem, number 10. Number 10, I'm going to break this up a little bit. This is a 3 times a 3. So what this really is 9 over the 4th root of 3 times x. So what I need is to multiply this by a 4th root of something that will make it perfect. So I need 4 3's and an exponent divisible by 4. So 3 times 3 times 3 times 3, that's 4 3's. And x times x times x times x, so x cubed. And the same thing on top. 3 times 3 is 9, so I'm just going to make this 9x cubed on the top. So when I multiply straight across, I get 9 times the 4th root of 9x cubed. When I multiply on the bottom, the 4th root of 3 times 3 times 3 times 3 times x times x times x times x is just 3x. And I notice again that I have a 9 over 3. That's like a fraction, so I can simplify. 9 divided by 3 is 3. Then I have 3 4th roots of 9x cubed over x.